In section 2.8, we're also looking at inverse functions, but we're going to be looking at them through equations and graphs. So we were looking at them primarily numerically in the last section. So our first objective is to determine the equation of an inverse function. So that's going to be our algebraic. Then we're going to look at the relationship between the graphs of inverse functions, and then we're going to determine the graph of the inverse function. So that'll be our graphical method. And then we're going to use calculator or decimals to produce graphs of inverse functions. All right. So in 2.5, we used the formula F equals 32 plus 1.8 C to convert temperature from Celsius to degrees Fahrenheit. Identify the input and output for this function. So we're going to call this function T. So I will rewrite it as T of C, since C is the input variable, equals 32 plus 1.8 C. In this function, the input is C, it's temperature in degrees Fahrenheit. So C, temperatures in degrees Celsius. And then the output, my mind had already moved on. My output is temperature in degrees Fahrenheit. So the units is what I'm putting down here. Temperature in degrees Celsius for C, temperature in degrees Fahrenheit for the output. So determine T of -5 and explain its meaning. So T of -5, I'm going to have 32 plus 1.8 times -5, or I can go ahead and just input this function. And I should see that T of -5 is 23. And so this means that -5 degrees Celsius is equal to 23 degrees Fahrenheit. So that would be the explanation of its meaning, putting the units with those values. When the temperature is 70 degrees Fahrenheit, what is the temperature in degrees Celsius? So 70 is an output value here. So I'll plug 70 in for F, equals the 32 plus 1.8 C. Move my decimals out of the way. And I'm going to need to subtract 32 from both sides. So that should give me 38 equals 1.8 C. And then I'm going to need to divide off that 1.8. So if I take 38 and I divide it by 1.8, I get 21.11 repeating degrees Celsius, about 21.11 degrees Celsius. All right, so we need to determine the temperature in Celsius for several Fahrenheit temperatures. So it would be nice to write the function. So instead of plugging in a number for our F, we're going to keep F as the letter F, and we're going to solve this equation for C to write the new function. So we're still going to do the same process. Subtract 32 from both sides, but instead of being able to combine those two numbers, when I do F minus 32, it's just F minus 32 equals 1.8 C. And then if I divide by the 1.8, I'll get our function. So there's two ways that I could write this. I could just leave it as that fraction, F minus 32 over 1.8, dividing that entire side by 1.8. Or I could distribute the division. If I distribute the division, I'm going to make sure that I take the imaginary 1 that's in front of this F, because there's a coefficient 1 right here, and I would divide 1 by 1.8. So I'm going to do that also. I'll grab my decimals over here, and I'm going to take 1 divided by 1.8. It's repeating, so I'm going to flip it into the fraction 5/9. So my C function would be 5/9 F minus, we'll do the same thing for our 32. 32 divided by 1.8 is 169. So depending on if you're more comfortable with the decimal in the denominator or with the fraction form, you could write this function either way. I'm going to guess that for right now, we're probably more comfortable with the initial version. So I'm going to keep my function written like this for the next couple of questions. Okay. I did want to do the other one because this is a linear function, and when it is rewritten this way, I can see its slope as 5/9 f. So if I did have a different context situation where a slope was something I wanted to talk about, it's important to know that I could distribute this denominator to see the slope and to see the vertical intercept. That's why I wanted to do this illustration. For this example, that's not part of our conversation, so it's okay to leave it unsimplified. Okay, so identify the input and output values for h. So I'm going to rename this h now. So they want me to call this h, and h's input variable is f. I just don't have room to write it in this space. I'm going to write it in my margin. And h of f is equal to f minus 32, all divided by 1.8. Okay, that's our h of f function that goes in here. All my work to solve for c, and then rewrite it with its new name h, because I said call it h. I identify the input and output variables for h. Okay, so the input variable is degrees Fahrenheit, and the output variable is degrees Celsius. So this is the inverse function, as up here, our input was degrees Celsius, that's our output down here, and vice versa, our output and our input are the same. So we have that swapped relationship for the inverse function. Determine h of 62 and its meaning. All right, so I'm going to go ahead, clean this thing up a little bit, and enter my h function. H of f equals the fraction f minus 32 divided by 1.8, and then I can evaluate h of 62. And since temperature, it's going to make more sense for me to explain that as 16.66 or 16.67 degrees rather than making this into a fraction. I don't want to say, if you told someone the temperature was 53rds degrees, they would not understand it as well as if you told them it was 16.7 degrees. So I'm even going to run it to one place. And that's in degrees Celsius, since the output is degrees Celsius. So what this means is that 62 degrees Fahrenheit is equal to 16.7 degrees Celsius. All right, moving that out of my way for a moment. So if we compare the process in part B and part 2, this was another one where I had a temperature in degrees Fahrenheit. I had a temperature in degrees Fahrenheit, and I wanted to get the temperature in degrees Celsius. So if I only had the original function, I would have had to plug the 70 in for output and solve for C. There were many steps. But in the inverse function, I can just plug 62 in directly and get the output. So it's a lot easier to use the inverse function because I have an input instead of having an output. All right, next we have determine t of 10. That's our original function, t of 10. Okay, so I still have that t function up here. And t of 10 is 50. Then I want h of t of 10. And so since I just discovered that t of 10 is 50, now I need to know what h of 50 is, right? T of 10 is 50. So what is h of 50? It's 10, which should not surprise us. We saw this in the last section as well. What we've done here is take a map from 10 to 50 with the t function, and then because h is its inverse, we mapped back with the h function. So we are ending up at 10. We went from 10 to 50 and back from 50 to 10. Okay, move decimals out of our way again. Determine each of the following. Now, I'm not going to plug these into Desmos because I know that these two functions are inverses. So I know that when I do h of 95, wherever it goes in degrees Celsius, when I plug that back into the original formula, I'm getting 95. We can check them if you'd like, but I'm going to get 95. So I'm imagining this map of 95 to something, and that something mapping back to 95. I don't have to know what I'm mapping to know that this happens because those two functions are inverses. We'll prove it in a second. I know this one's going to be 0. I know this one's going to be 212 because I know those two functions are inverses. And in general, h of t of c is going to map back to c, and vice versa. T of h of f is going to map back to f. So we can check if I am doing t of h of 95, that would put 95 into h. The output is 35. Then it would put 35 into t. I get 995 back. If I did h of t of 0, 0 goes into the inner function t first. Then 32 goes into the outer function h. I'm back to 0. And the last one, t of h of 212. 212 goes into the inner function h. I get 100. And when 100 goes into the outer function t, I get back to my 212. So I do get the input back out when I compose it, the function with its inverse. Okay, so we double checked that there. All right, so here we go. Based on the results of parts A and B, what do you conclude about the functions? Oh, they're inverses. We already knew that they were inverses, I hope. But this is how we show that the two functions are inverses, because when you compose them in either order, whatever the input is comes back out. All right. So more generally over here, this is the process for finding the inverse function. If it's in function notation, stick it in equation notation is what they're saying here. So put in a y instead of an f of x. And then solve the equation for x. Whatever the independent variable is, solve for it. Then rewrite in function notation. If you're in a non-contextual abstract situation, you can switch x and y so that your new input is called x. We did not do that in the case of the temperature because we didn't want to switch the meaning of what the letters were. C meant Celsius, the letter C meant something, but if it's just x and y, they're arbitrary letters, so we do switch them in the non-contextual cases. So we'll see how that works in number 8 here. So I have y, or f of x, equals 5x minus 3. I'm going to start by writing in equation notation. Don't write the function part, just the equation part. Y equals 5x plus 3. So write it in terms of x and y. That's our first step. And then it says to solve for x. So I want to get x by itself. So I'm going to subtract off that 5. And I'll have y minus 5 equals negative 3x. And we'll divide everything by negative 3. Now, this is an instance where I am going to distribute the division like I did over here. And the reason is because this function's a linear function. It's not in a contextual situation like this one was. I'm going to want to know its slope, and I'm going to want to know its y-intercept. So I did it over here just for some practice. We're going to do it here for sure. In this example, you can tell that it's linear because the original function was linear. So the inverse function is going to be in that same format. So I have this y right here. It has its coefficient 1. And so if you take 1 divided by negative 3, that's going to get you negative 1/3 y. And then 2 negatives, this will be a positive, and then 5 divided by 3 just simplifies as 5/3. Then I have my x by itself. I did distribute that division there. Okay, so that finishes step 2, solve for x. Step 3 is going to switch the letters and get it into function notation. So if I switch the letters, this will be 1/3 x plus 5/3. I didn't say the negative out loud, I meant negative 1/3. And then we're going to rewrite it in function notation. So instead of calling it y, we're going to go back to the name f, but now this function is f inverse of x equals our negative 1/3 x plus 5/3. And that is our inverse function. All right, so we're going to hang on to that for a second. We're going to talk about graphs of inverse functions with these two, and then I'll talk back about the graph of this one just for fun. So consider the graphs of these two functions on the same coordinate system. Instead of drawing them down here, I'm going to graph them in Desmos. Okay, and my first function is f, and it's equal to 7 plus 5x. My next function is f inverse. I can't type f inverse into Desmos because it would think that the -1 was a power. That's okay. I'm just going to call it g of x instead. When I type it into Desmos, just give it a new name. It's still the inverse, but I'm not going to use that inverse notation. So my new function is called g of x, and it's supposed to be x minus 7 over 5. All right, so we want to look at the graph part here. And that's what I see. When I get to the next page, it says draw the graph y equals x on the same grid. So I'll graph y equals x. I'm going to dot that in. So what we're trying to show here with the graphs of the inverse functions is that there is some symmetry across the line y equals x, where they're equally spaced around y equals x. So if you fold it along this line, then the graph of the function, the graph of its inverse would be the same. They would line up. Okay, so you can see that they're the same distance diagonally across this line. That's what we should be observing. So I'm going to check this with the other two functions that we just did as well. I'm going to keep my y equals x there. For number 8, our original function was f of x equals 5 minus 3x. And our inverse function I'll call g of x was negative 1/3 x plus 5/3. So again, you should be able to see some symmetry. These two lines look different than the other two, but there's still the symmetry. Kind of looks like a dragonfly to me, something like that. But there is some symmetry right here where they're equally spaced around the y equals x line. Why is it y equals x? That's because when we are trying to find the inverse function, we're replacing y with x. Y becomes equal to x and vice versa. X becomes equal to y. That's how we find the inverse function. We're swapping x and y. Okay. All right. Oh, yeah. So the next part is about how to get inverses to draw. There's a bunch of calculator stuff that we're going to ignore, but we can do it even better on Desmos. So we're going to do some playing on Desmos to get graphs of inverse functions to draw. Okay, so even better, let me make this a little bigger. If I don't know what the inverse function is, I'm going to actually take the f of x out for a moment and just put a y in because that's the same thing. The very first thing you do when you want to write the inverse function is you switch the letters. Now, we actually solved for x and then switch the letters, but you could switch them first. If I just switch the letters, x equals 5 minus 3y. That's already the inverse function. It's just not solved for y yet. So I can graph, and you'll see that this shows up at the same place. If I dot this one or make this one dashed here, you'll see that it's the same as the function that we did get when we solved for the inverse here. So if you just wanted to see the inverse but not actually know what its equation is, swapping the letters would be sufficient. So I'm going to hide these examples and make something up. Let's say I make up a function like y equals the square root of x plus 4, say, and I wanted to see what its inverse looks like, then I would just swap the letters and do x equals the square root of y plus 4. Cool. So again, I have a function and I have its inverse. These are both functions. I have a function here and its inverse here. They both pass the vertical line test, so they are two functions, and you can see the symmetry. So I can graph a function and its inverse on Desmos even if I don't know what the equation would be if I solve for it. So I would need to solve for y to find this in function notation to find the algebraic inverse, but I can get its graphical inverse just by switching the letters. So there's a bunch of weird calculated directions that don't involve switching the letters, that involve something weird. But in Desmos, it's much easier. Just swap the letters, you can see the function. One of the cool things is you can even do this if it's not going to give you a function as its inverse, if it's going to give you something that's not a function. So I'm going to do a quadratic. Let's say I do, or maybe a cubic just for fun. Let's say I do y equals x to the third minus 2x squared. That's good enough. Looks pretty. And I'm going to graph its inverse. So it's going to be x equals y to the third minus 2y squared. So again, really cool shape here. You can see that they're inverses, but you can also clearly see, if you think about graphing x equals negative a half or something, that the inverse, this line right here, is not a function because it would not pass the vertical line test. I was able to graph it anyway, even though it's not a function. It's a relation. This is the inverse relation. So there's not a true inverse to this function here. It doesn't have a true inverse, but I can still graph a picture of what its inverse relation would look like. That's something the calculators don't do so well. So Desmos can do that, and I think it's kind of fun. So I wanted to show some additional examples there. Okay, enough on that. Let's finish up our section back over here. We are looking at, what are we doing? Determine the point of intersection of the graphs of f and f inverse. Are we still using, yes, we're still using those. Okay, so let me go back to those two functions that they had asked us to use right here. Determine the intersection point. So the intersection point is at negative 1.75, comma, negative 1.75. What is the significance of the point in this situation? So the function and its inverse are equal. They could only ever be equal if the x value and the y value was the same, because the input and the output have to equal. When you have a function and their inverse, one of them outputs input, one of them outputs output. So they have to be equal. So the input has to equal the output in order for them to be equal. Okay. Okay, and now we're going to find the horizontal and the vertical intercepts for these two graphs. I'm going to hide the y equals x just for a moment. Pull this down. So the first function, that is this one, I want to know its vertical intercept. Its vertical intercept is at 0, 7. And its horizontal intercept is at negative 1.4, comma 0. And now the other function, this function here, its vertical intercept is at 0, comma negative 1.4. And its horizontal intercept is at 7, comma 0. So again, input and output switch places. So you can see the relationship here between the vertical intercept of one function and the horizontal intercept of the other function. If you switch 0, 7 to 7, 0, it would go from being a vertical intercept to being a horizontal intercept. And vice versa, of course. If you switch negative 1.4, comma 0 to 0, comma negative 1.4, it would go from being a horizontal intercept to being a vertical intercept for the inverse. Write a sentence that describes the relationship between the inverses. I'll let you write your own sentence for that. I was just talking about it out loud right here and about that relationship that we see. And so for number 12, determine the slopes of the graphs. Okay. If I go back and look at their equations, I can see that the slope of the graph of f is 5. Okay, so for f, m is 5. And for f inverse, they didn't distribute for me. I wish they had. So now I'm going to go ahead and distribute for f inverse here. That 5 needs to go underneath both the x and the 7. So this is 1x over 5 minus 7 over 5. And so I can see that the slope of this one now is 1/5. That's why we distributed when we did our own example. I didn't finish it, so we had to do that step when we wanted to talk about slope. So the slope is 1/5. So the relationship between these slopes, one is increasing at a rate of 5 over 1, rising 5, running 1. The other one's the reverse, rising 1, running 5. They are reciprocals. Reciprocals means that they're flipped. So 5 over 1 versus 1 over 5. The slopes are reciprocals. Okay, and last, number 13, there's a graph here, and I don't know the equation for this graph, so I just want to draw its inverse. So I know that I need to be symmetric across y equals x. I drew y equals x in for me. And any point that I have, I can flip the coordinates to find another point. So for example, here, this is the point 1, 0. So I should have corresponding the point 0, 1. And you can see they're equidistant across y equals x. If I look at this point right here, this is the point 6, 2. So I should have the point 2, 6. And those would be equidistant. Okay, then I get really, really close to, but don't touch the y-axis. So I should get really, really close to and don't touch the x-axis. And this would be what the inverse should look like. You can see symmetry, equally spaced from here to here, equally spaced across y equals x. All right, so we'll do this again. We have our function and we have our y equals x. Again, this line is just showing you your line of symmetry, y equals x here. That's our function f. All right, so some of the points we have. This is a point at 0, 2. So my inverse function is going to have 2, 0. This is a point here at 3, 0. So I'm going to have 0, 3. I can do a couple more. This point right here would be 6, negative 2. So I'm going to have negative 2, 6. And this point right here would be negative 6, 6. So I'm going to have 6, negative 6. And so we can connect these to see the inverse function. And we should be able to see symmetry. When I see symmetry, I see that these points are symmetric. They're equally spaced. And I can see that these points are symmetric. They're equally spaced. That's what I'm seeing with the symmetry here. Okay. We get to do that one more time on the next page, and that's our last one. Okay, anytime I'm touching the line y equals x, that point is going to be both on my function and on its inverse. So my function is going to have those 3 points. I'm not going to draw too many other points. I'm going to do this one a little more visually. So I go under this little bubble right here. I have to be symmetric, so I'm going to have a little bubble on this side, right? So they have to be equally spaced around y equals x. So this side, I'm going to have another little bubble on this side, equally spaced, right? So my inverse does this. Now I'm curving away, okay? So I am curving away, and I'm going to curve away here as well. And so I went a little too far with my curve. It should be right up here. So I should be equally spaced. This curve really should be hitting right here. My marker was a little touchy there. I should be curving away so that I'm equally spaced. If you're looking at the top border of this, I'd be about equally spaced right here and here. So my function, let me just draw it with a darker color here, would be like this for the inverse.